Hello everyone and welcome to lecture 10 of the course on diffusion models. I am Dheeraj Madan and today we will be studying denoising diffusion implicit models. Right? As the title of the lecture suggests, so this is the paper we are going to look at today, and I'll post a link to this in the description box below. So we have already studied, DDPMs, and for some time we were looking at score-based models, and then we had a look at the connection between the two, and then we also looked at stochastic differential equation, right? And then how it connects everything all put together. So here this lecture is going to be a slight sort of slightly different from we'll take a slightly different track today. And in fact, hopefully this is going to be the last lecture of this course. So here we'll essentially be looking at DDIMs, right, or denoising diffusion implicit models. And the motivation for this is that the DDPMs which we studied so far, so essentially they require a large number of sampling steps, right? So even if we have trained the model, right, if we want to do efficient inferencing, then it becomes difficult with these models because these have large number of sampling steps at inference time. So the question is that, so can we make this inference faster? And essentially what this paper proposes to do is that here they propose, the main idea here is that we consider a large family of forward distributions forward distribution. So basically this is essentially the posterior distribution or the sort of forward Markov chain. So forward Markov chain or posterior distribution. Actually this here actually will be losing out on this Markovian property. We'll just see, but I'll just call it forward network for now. Just the posterior distribution that gives rise to the same training objectives as DDPMs. So why is it useful? Firstly, this cuts short the number of steps for reverse process. And secondly, this makes reverse process deterministic as well. So we'll just see this now. Okay. So let's recall the idea of DDPMs first. So essentially, in case of DDPMs, what we have is that we have a sort of a forward process which is essentially a Markov chain. For DDPMs, we will show how to give up this assumption of Markovian property. So we have the sequence of variables x1 up to xt. Okay, so x0 is essentially my data, and for these posterior variables we model the distribution as a sort of forward as a Markov chain, wherein we have that q of xt given xt minus 1 is normally distributed with mean square root of alpha t xt minus 1 and variance 1 minus alpha t times identity. Okay. So this is how we have the sequence of forward step, and the reverse Markov chain essentially we have xt which starts from a normal distribution. So here xt, in the end we should get a normal distribution, right? And then we have this reverse sequence of steps leading up to x0, which is our theta. And here each step we model as p theta xt minus 1 given xt. Okay. So note that from the forward process, we define q of xt given xt minus 1, but we can also derive that q of xt given x0. Okay, so here we can actually derive q of xt given x0 is also normally distributed with mean alpha t bar x0 and variance 1 minus alpha t bar identity. Okay. So alpha t bar is product of I from 1 to t alpha I, right? We have seen this multiple times, so I'm not going to write it down. So here essentially, for the sort of forward process, we actually also have this sort of reparameterization, which we are going to use a lot today, which is that xt is essentially square root alpha t bar x0 plus square root of 1 minus alpha t bar times epsilon t, where epsilon t is normally distributed with mean 0 and covariance identity. Okay, and here essentially let's also rederive the objective, because we'll actually have to modify that same sort of derivation. So let's rederive the sort of objective function also. So here our objective function is to maximize with respect to parameters of the likelihood distribution. So this reverse Markov chain is defining a likelihood distribution which is parameterized by these parameters theta. Whereas the forward process, this does not have any parameters at all. So we have to maximize with respect to theta the elbow as a function of theta. And how do we have this elbow? So this elbow is nothing but expectation of q of x1 up to xt given x0 log p theta x0 up to xt over q of x1 up to xt given x0. Okay, and now what we do is that we factorize both numerator and denominator. So what we get is p theta xt, p theta xt minus 1 given xt up to p theta x0 given x1. And we also now try to factorize the denominator in a similar form. So we write it as q of xt given x0, q of xt minus 1 given xt x0, and so on until q of x1 given x2 x0. Okay. Now if we start combining the terms, and we can break this log of product into sum of logs, so that will give us essentially so essentially that will firstly from this thing we'll get this prior matching term. Okay, which is essentially minus the KL divergence between q of xt given x0 and p theta xt, right? So this will not have any parameters at all, so we can actually ignore this term also. But coming back to the remaining objective function, so from these terms, right, so we are going to get sum over all small t and then minus of KL divergence between q of xt minus 1 given xt x0 and xt minus 1 given xt x0 and p theta of xt minus 1 given xt. And here small t is summed up to capital T and it starts from 2. right? So 2 to capital T. But note that we also have to, this KL divergence will essentially take expectation over xt minus 1, but we also have to take expectation of xt given x naught also. So outside this these KL terms, we have expectation of q of xt given x naught of this quantity. And then finally, there is one term which is left over. So this is essentially the same term which we have in the sort. So these terms, they essentially they match the sort of so they essentially match the forward and the backward steps together, and this essentially matches the prior. And then there is also a reconstruction term which maximizes expectation over q log p theta x naught given x1. So okay, now how do we sort of model this thing? So this distribution, right? So this we can derive it as a form of a normal distribution, and the mean and the sort of the mean can be derived as a function of xt and x naught, and covariance is just a fixed function of alphas that does not even depend on xt and x naught. And we model p theta of xt minus 1 given xt also as a normal distribution with a parameterized mean and the same sort of covariance matrix. But here, then computing the sort of KL or essentially sort of maximizing the negative of KL, which is equivalent to minimizing the sort of KL distribution, because you're maximizing negative of KL, that corresponds to minimizing the squared norm of the difference between the actual mean as a function of xt x naught and the produced mean. And since this actual mean is a linear combination of xt x naught, so if we model the sort of mean as a function, as a parameterized by theta as a function of xt, that will have an xt term, and then there'll be some addition of some coefficient times x naught. So overall, this is equivalent to minimizing the sort of x naught hat. So basically there's a network which is going to produce this estimation of x naught in terms of xt parameterized by theta minus the actual x naught squared, right? So this thing take an expectation of xt given x naught, right? And here essentially we can also show that this is equivalent to minimizing over theta epsilon naught. So there is a network for epsilon naught hat as a function of xt and theta minus the actual epsilon naught squared. Or actually I should call it epsilon t, right? So basically epsilon t is this reparameter. It comes from this sort of reparameterization here, right? So we are trying to predict x naught, which is equivalent to predicting the noise, because essentially if you know the sort of noise, you can subtract it back and recover x naught also. So overall, the objective function then translates to, so actually it's essentially a repetition, but I just wanted to go over it again so that this sets up the notation and all for today's lecture also. So here essentially we have this sort of objective function, which is sum over t gamma t expectation of x naught given q, x naught coming from q of x naught and epsilon t from some normal distribution. So this is essentially sampled from data. X naught is sampled from data, then you sample some noise, and then essentially you try to recover this noise, okay, from xt. So how do you get xt? By adding this sort of noise and x naught together. It's in this particular way. So this is the expression for xt. So epsilon theta. So you compute xt and then you try to recover the noise through this network, and then you try to minimize the sort of difference with the actual noise squared, right? So this noise which was added to it. So this was our objective. So this is something which we train. Now at inference time, what can we do? So the idea which we look at is that we try to look for other sort of such processes which have the same sort of objective function. So here's the question. So what other families of distribution give rise to the same objective. Okay, so here essentially we want two necessary and sufficient conditions. So firstly, we must have that Q of xt given x naught, right? So here when we are looking at families of distribution, this is the family of posterior distribution, as in the forward process. So I'm not writing forward Markov chain because we will be giving up the Markovian assumption now. So what we want is that Q of xt given x naught, right? So since I want the same objective function, so here essentially still I should be producing xt from the same sort of distribution. So this must be same as something with mean square root of alpha t bar x naught and variance 1 minus alpha t bar identity. Second thing what I want is that how we actually got to this thing, right? So we actually first expressed this as a squared norm of the difference between the means, and which was equivalent to difference between x naughts, which was essentially equivalent to difference between the epsilons, right? So the reason why it's a difference between epsilons is justified from the first equation itself. But how do you go from difference between means to difference between x naughts? And that you can always do provided your Q of xt minus 1 given xt x naught, right? So this distribution, this must be modeled as some sort of normal distribution, which is a sort of a coefficient which essentially is a linear combination. So the variance here I can allow it to be any variance, okay, but the mean essentially should be some function, okay. So some function of let me just say at minus 1 x naught plus bt minus 1 xt. So this should how my mean should look like, right? So it's a linear combination of x naught and xt. Actually, I'm not going to call it bt minus 1. Let me call it ct minus 1. I'll reserve bt minus 1 for something else, which I'll just write right now. So I'll just call it ct minus 1. But if what I do is that for simplicity, I say that okay, these coefficients, I instead of modeling it as x naught and xt, as linear combination of x naught and xt, I directly model it as a linear combination of x naught and some epsilon t, some notion of epsilon t. So what we actually do is that instead of modeling this, okay, so what we change it to is that Q of xt minus 1 given xt x naught is normal distribution with mean at minus 1 x naught plus bt minus 1 times xt minus square root alpha t bar x naught over 1 minus alpha t bar. So this is essentially the actual epsilon t. So it's a linear combination of x naught and epsilon t, and but you can see, right, so any linear combination of x naught and this sort of epsilon t can be written as a linear combination of xt and x naught, and vice versa is also true. So this is not something strange we are doing, and then a variance term which is sigma t square identity. So these are the two assumptions I'm making, right? And if you have these assumptions, you are going to get an objective function of similar form. Okay, maybe with these coefficients might change, these gamma t coefficients, right? But that's fine for me. Okay, so how do I satisfy the two assumptions together? So note that the second assumption is actually telling me something more, isn't it? It's actually a sort of a stronger assumption than the first one, because from this thing we can actually we'll actually try to sort of see that how do we get to the first condition. So it's not exactly stronger, but somehow if you define your distribution xt minus 1 given xt x naught, then you can actually move to distribution of xt given x naught also. So let's see if we do that, what do we get? Is assumption 1 satisfied or not? Okay, by the way, from the second part, not only q of xt minus 1 given xt x naught, I also need q of x capital T given x naught, right? That is essentially coming from the first one. Okay, so let's see. So from the first assumption, we already know what is x capital T given x naught, right? Right, so this is what I already know. Now from the second assumption, let me see how do I satisfy it. So from the second assumption, what I have is that q of x capital T minus 1 given x capital T and x naught. Okay, so this is normally distributed with mean a capital T minus 1 x naught plus b capital T minus 1, okay, x capital T minus root of alpha t bar x naught, okay, over 1 minus alpha t bar, and variance is sigma t square identity, right? So since xt is coming from this sort of distribution, so I can write xt as square root of alpha t bar x naught plus square root of 1 minus alpha t bar times epsilon t. So substituting it here, what we have is that, and essentially from the second one, what we have is that xt minus 1 equals so mean plus sigma t times some zt. So essentially at minus 1 x naught. So here also again I am trying to do reparameterization here, plus bt minus 1 xt minus square root alpha t bar x naught over square root 1 minus alpha t bar, okay, plus sigma t zt, where zt is coming from standard normal, right? So here this thing, right, from this equation, this is nothing but epsilon t, where epsilon t is standard normal, right? And that was the reason why I parameterized it in terms of epsilon t rather than the first one. Now let's see what's the mean of xt minus 1. So firstly, here essentially xt minus 1 is x naught, which is fixed, plus some linear combination of epsilon t and zt. So since both of these are standard normal, so their sum is also going to be standard normal, and the mean of xt minus 1 is essentially going to be the expectation of at minus 1 times x naught. Okay, so xt minus 1 given x naught. Okay, so x naught is given to me. So at minus 1 x naught plus bt minus 1 times this mean. So bt minus 1 times 0 plus sigma t times 0. So essentially this mean is just going to be at minus 1 x naught, right? But what should this have been ideally? So ideally this should have been equal to square root of alpha t bar x naught. So these two must be equal. So therefore at minus 1 must be equal to square root of alpha t. Alpha t minus 1 bar. Yeah. And from the second equation, what do I get is that so for the second part, what do I need is that I need to check, for the second part is to compute bt minus 1. What I need is that I need to look at the variance of xt minus 1 given x naught. So the variance of this is going to be, so this is a constant given x naught, so which equals bt minus 1 squared times the variance of epsilon t, which is 1, plus sigma t squared times the variance of zt, which is also 1. And what should ideally be equal to? This should be equal to 1 minus alpha t bar. So this gives us that bt minus 1 equals 1 minus alpha t. This is alpha t minus 1 bar, right? So 1 minus alpha t minus 1 bar minus sigma t square, right? The square root of this. Right. So this is how I get 80 minus 1 and bt minus 1. And actually I'm doing this, for capital T, but we can actually essentially do it for any type of small t also. If I have replaced capital T by small t, it generalizes. So essentially the sort of distribution we can, putting the two distributions together, the distributions must choose should be q of xt minus 1 given xt x naught should be normally distributed with mean square root alpha t minus 1 bar x naught plus square root of 1 minus alpha t minus 1 bar minus sigma t square times this times this thing epsilon t, right? So xt minus square root alpha t bar x naught over square root of 1 minus alpha t bar, right? And with variance sigma t square identity. So this is the sort of distribution I want, right? So I have to specify this distribution for q of x capital T given x naught, and then all these sort of transitions. So overall, the way I'm specifying the distribution is that I have to sample x naught, then given x naught I have to sample xt given x naught, and then given xt and x naught I have to sample xt minus 1, then given x naught and xt minus 1 I have to sample xt minus 2, up to so on until we get x1, right? So this is how I'm defining my sort of forward process. So note that this is not Markovian because we also condition on x naught every time. And now if we model the sort of reverse distribution, which is the likelihood as p theta of xt minus 1 given xt as normally distributed with mean square root alpha t minus 1 bar x naught as a function of xt plus square root of 1 minus alpha t minus 1 bar minus sigma t square times this epsilon theta hat as a function of xt and variance sigma t square identity. So here essentially x naught hat as a function of t can also be expressed in terms of epsilon theta using the same reparameterization. This one. Right, so x naught is nothing but xt minus square root alpha t square root of 1 minus alpha t bar epsilon t over square root alpha t bar. Right, so you can write it as in terms of epsilon theta, right? So that's a homework for you, so I'm not going to do that, and I'm also leaving it as a homework exercise for you to generalize from capital T to in general small t. You have to show that how AT minus 1 and BT minus 1 they are as we have calculated. Okay, so homework generalize to arbitrary t. It's actually the same calculation works. So essentially what we have done so far is that we have generalized the class of distributions from the forward chain, and then we have shown that the same objective entrant you can now sample from any sort of Q distribution which comes from this family, assuming that your model for p theta is as follows. Okay, so here let me just write it down here. So essentially xt is square root of alpha t bar x naught plus square root of 1 minus alpha t bar times epsilon theta, right? So essentially what we have is that x naught parameterized by theta as a function of xt is nothing but xt minus square root of 1 minus alpha t bar epsilon theta over square root alpha t bar. So this is what we have to substitute here. Okay, so essentially using this thing now you can start from t equals capital T and then successively sample xt minus 1, xt minus 2, so on, using this sort of sampling, wherein now the only additional thing we have is that now here freedom, this sigma t square freedom is there, right, which you didn't have earlier. Okay, so what happens is that, okay, why is it important? So firstly I said that I can make the process deterministic. So essentially when sigma t equals to 0, right, so this is a deterministic process because then the variance will be 0, right? So in the limit of sigma t tending to 0, we get a deterministic sort of forward process. And in this case, the reverse process is also deterministic because this also has the same variance term. So we get a deterministic process, right, for inference. Right, and this makes the training faster. Second thing is that which we want to discuss. Okay, in general, these class of models, they are called as DDIM. So here you have this flexibility of choosing sigma t, and if you choose sigma t appropriately, you can even get to the usual DDPM process also. Okay, so homework exercise, homework 2. So what values of sigma t give me original DDPM. So for DDPM also we can derive an expression for q of xt minus 1 given xt x naught, and then you just have to match them. So you can get you can find out the sigma t which gives you the original DDPM also. That's okay. So the second contribution of this paper is that of accelerated generation. So let's say, suppose t is large. So how to sample efficiently? Okay, so essentially we need to select a subsequence tau 1 up to tau s just t as a subset of 1 up to capital T. And now we define a process which gives us the similar training objective but on this subsequence. Okay, so define a forward process which gives the same objective as DDPM but defined on this sequence. So let's see. So DDPM has to be defined on the full sequence, but the R process will be defined on this subsequence, but then still they will have the same training objective. So is there such a sort of objective function? Is there such a sort of this forward process, right? So the idea is that, well, we essentially the way this paper defined it, they actually did it in a more general way. So they actually did this for DDIM. And as a special case, since DDPM also follows a special case of DDIM, so this automatically follows from there. So how is this process defined? So in this process, we have x naught, okay, and then conditioned on x naught, what I have is that q x of tau s, right, which is x of capital T, and then condition of x on tau s and x naught, I have x of tau s minus 1. And then conditioned on this thing and x naught, I have x of tau s minus 2 up to so on until x of tau 0. Right, so this is how I define my but now there are other variables also, right? I have to define it. So I condition all of them directly on x naught. So xt for t not in the sequence tau 1 up to tau s. So I just have this conditional of xt given x naught. So overall, the way we are defining this distribution, so this is the forward process. So overall, the way I have defined the distribution q of x1 up to xt given x naught, this is essentially product over I q of x tau I given x tau I minus 1 and x naught. Okay, actually first I have to define x tau s given x naught and then I can do this thing. Okay, so q of x tau s given x naught, then product over I q of x tau I given x tau I minus 1 and I going from wait, it has to be tau I minus 1 given tau I, right? From 1 up to s. So tau 0 given x tau I minus 1 given x tau I and x naught, right? Right. And then product of t not in tau 1 up to tau s q of xt x naught. And for each of them, okay, now what I do is that I define these distributions similar to DDIM. Okay, the way we derived the expression. And for xt given x naught, this is also similar to DDIM, but for this thing, I just define this as square root of alpha t bar x naught with variance 1 minus alpha t bar identity. Okay, so I have defined this distribution q of xt given x naught separately, and these are defined in a Markov chain. So this is how my Bayesian network is going to look like. Now for the reverse process, what I have is that I need to start from xt, which is x tau s, which is normally distributed with mean 0 and covariance identity, and then I go all the way back till finally I have x tau 0 and then x naught, and then I have xt given x naught for t naught and tau. Right. So this is the reverse Markov chain. Now if we try to write down the elbow, this is nothing but expectation of q of x1 up to xt given x naught log p theta of x naught up to xt divided by q of x1 up to xt given x naught. Okay, and now I split these terms. Essentially here I have p theta of x tau s, which is nothing but xt, which is standard normal, and then the product, so basically p theta of x tau s minus 1 given x tau s to so on until p theta of x tau 1 given x tau naught, and then p theta of x naught given x tau naught. And then finally I have the product of t naught and tau p theta of xt given x naught. This is the numerator. And similarly in the denominator, I am going to get q of x tau s given x naught, okay, and then q of x tau s minus 1 given x tau s and x naught, so on until q of x tau naught given x tau 1 and x naught, and then product of t naught and tau q of xt given x naught. So what I'll do is that I'll combine these terms together, t naught and tau. For every t I'll combine them together, and so I'll combine x tau s, p theta x tau s with q of x tau s given x naught, and then all these terms p theta of x tau I minus 1 given tau I will combine with q of x tau I minus 1 given tau I and x naught. And then I'm again going to get those scale divergences, and then I have to model the p theta distribution appropriately to give me the same sort of objective function. So essentially we are going to now maximize with respect to theta minus sum over t naught and tau KL divergence between q of x sort of t given x naught and p theta of xt given x naught. So if I model both of them as sort of the so what I can do is that for these terms essentially both of these can be modeled using the same form, that mean square root alpha t bar x naught and variance 1 minus alpha t bar identity. So this does not have any parameters at all, and combine with the other term, right? So KL between q of x capital T given x naught and p theta of x capital T, similar to the earlier terms we had like this. So all these terms will go off to 0, including this one. Right, so all these terms will go off to 0. But there will be some more terms, which is minus sum of I from 1 to s, KL between q of x tau I minus 1 given x tau I and x naught, right? So expectation of this, from and p theta of x tau I minus 1 given x tau I, right? So these terms will be there, right? So expectation of these terms over x1 given x naught, x tau I given x naught, right? And then there is this term of expectation of x of tau naught given x naught of log p theta of x naught given x tau naught. Okay, so just verify, okay, so model p theta appropriately and then show that, so this is homework 3, show that this gives the same objective function. DDIM, right? And if you model p theta appropriately, then it will be a DDPM also. So essentially what you can do is that once you have trained your network, you want to do a faster efficient inference, then what you can do is that you can cut short the number of steps at inference time, and then again you will be able to retrieve the same sort of distribution, right? So this was what we had for this particular course. So yeah, I'll post a link to this paper in the description box below, and this paper also has one more interesting aspect. They actually derive an ODE for this process, an ordinary differential equation, and show that it is equivalent to the one which was described in the Song et al.'s stochastic differential equation paper also. So that's another interesting contribution of this particular paper. And of course, they have all those experimental details as well. So do go through that, and thanks all. And this ends the course. Do let me know if there are other interesting papers or any other works you want me to discuss in some of the future courses, either extension of this course or any new course you want. So let me know. Okay, thanks. Bye.